Thanks for being with us here today. Could you tell us a bit about yourself and your work?
Yeah, so I'm a research scientist in the field of general relativity and gravitational wave science. I did an undergraduate degree at Monash University and honours in pure mathematics there, and then a PhD in relativity at the University of Adelaide. Then I spent 4 years working with Sir Roger Penrose at the University of Oxford. And I've come back to Australia, and I'm now at the Australian University and been there, for quite some time. Big things I'm working on now in gravitational wave science is we want to detect a new type of source that we haven't yet detected, and that would be from a continuous stream of gravitational waves from an object like a neutron star. Now, neutron stars are the densest type of star in the universe. And they're very small and dense, and quite honestly, they're very enigmatic. We don't really understand their properties, the nature of the material that makes up them, their exact measurements, like radius, mass, and so on. And we do believe that they are slightly misshapen, so they're a little bit squashed, and that produces a gravitational wave signal, which is continuous because the things continue spinning. Of course, it's much weaker than the sort of signals we've got so far. That's why we haven't detected it. We've detected the big collisions. But we do believe that we will, when we detect them, get a lot of new information about neutron stars and open up that field, which is kind of one of the last remaining fields of unknown matter, if you like. And it is, as I say, it's very interesting because it's the densest material in the universe.
So from my understanding, gravitational wave astronomy is a fairly new field. How would you say that it's developing?
First detection was at the end of 2015, and that was the very beginning, of course, our first detection of a gravitational wave event ever. And since then we've been sort of slowly cranking up, and the reason for that is, as time goes by, we make the instruments, the detectors, more sensitive. And that means we can reach out into a bigger volume of space and collect more events. We now have over 90 binary collisions of compact objects, mostly two black holes. We have a few sort of combinations, like two neutron stars or a black hole and a neutron star. As time goes by, we get a lot of information from those collisions about the lives of black holes and neutron stars throughout the universe. So we find out things like how many there are, how do they get together in pairs, what are their formation channels, what sort of spin rates can these objects have, and importantly, what kinds of mass ranges can they have. There's this very strange, enigmatic sort of mass range in the lower end where the things could be sort of black holes, very light black holes, or very heavy neutron stars. And we're still probing that like crazy because we don't know as yet what can be the heaviest neutron star. Also, we don't know what can be the lightest black hole. We know about the sizes of black holes coming from stellar collapse, but that's not the only potential start of black holes, ways that black holes are produced. And so it's possible, actually now we think we really have them, because for a start, if you take two neutron stars and they merge, then the thing you get is going to be too heavy to be a neutron star. So it's really got to be a black hole. And then it's going to be a pretty light black hole.
Right. And so it's sort of just narrowing down like that range of which the transition is.
Yeah, exactly. And also we're probing the other end of the black hole range, not the sort of million solar mass black hole type things, but the stellar mass black hole range. And we have just found in our recent run the first intermediate mass black hole. So that's the first one ever directly observed in that mass range, which is really exciting. So we know these can be produced by two stellar mass black holes colliding and producing an intermediate mass black hole. But beyond all that, as we get more sensitive, we will pick up sources which are weaker. And one of these is the sort of continuous wave stream that I talked about coming from neutron stars. So these other sources we have are burst sources, we only pick them up in their last, few cycles, and then they smash together, and we have a bit of time after that where we pick up a signal. But it can be 0.3 of a second. So that's why we call them bursts. But continuous waves, we can observe, if the observing run goes 1 or 2 years, we can observe a source like that over that whole period. So that helps us to build the signal and eventually, hopefully, get a detection. So there are new sources that we want to go for, and that's one of them, but also supernovae going off, for instance. And another really intriguing thing about gravitational waves is that we can declare unknown sources. We get a signal, gravitational wave signal, and it doesn't fit any of our predicted signals for the sources that we go for. So, like a binary merger, that sort of thing. But it means we've ruled out all other possibilities, like there's so many noise sources, it's ridiculous. But we've ruled them all out, and then we have a clear signal, a burst signal probably, and we won't know what it is. So that's going to be fantastic, because then we'll really have a big mystery and,
Unknown unknown.
And that's exactly it.
If you were to find something new right now, what would be your preferred discovery of the day?
Given the amount of work that I've been involved in my group and other people, I would love to detect continuous waves from a neutron star. I think that is a very exciting field to be opened up. It's going to answer a lot of questions, and I would love to see that happen sooner rather than later. We might get lucky in the next observing run, but there's no guarantee. We may have to wait until the third generation detectors, because they'll be about an order of magnitude more sensitive again.
So if you were to detect this continuous waveform from a neutron star, what kind of information would lead from that?
If we do it alone, or if we do it and then there's a counterpart for it in the EM spectrum, electromagnetic spectrum, then we can get different things from it. But, things like, we'd like to know more about the mass range for a start, the size, the radius. We'd like to know about the equation of state of a neutron star. And that's a big one. And, to find things like the moment of inertia and so on. We want to piece together as many of the properties as we can from hopefully 2 sets of observations from the 2 spectra. And we already are doing work to synthesize how we can use the equations to drag this information out from the signals once we get them.
In 2020, when you were part of the winning team for the Prime Minister's Prize for Science, what was the work that led to that?
Basically, we were 4 recipients, and we were the people who more or less started the field here in Australia. And this goes back a very long way, and of course the longest of all is David Blair from University of Western Australia. But the other 3 are instrumental people, experimental scientists, and they developed different aspects of components of the detectors, their teams, and contributed those to LIGO. So that was a very important contribution. And in about 1997, I started the data analysis science side of the project in Australia, which was the one that was missing at that time. And started in a small way in Canberra and slowly built that over the years. And we wrote a lot of the software to do with the LIGO data analysis system in the early days as it was being set up, but we did a lot of other development work to do with neutron stars. We ran searches for neutron stars, but we also developed other computing aspects. We looked at optimal detector placement around the world, because we've always got our mind on putting another one in Australia. We looked at lensing of gravitational waves and all kinds of other things. But the net result of all that was that by the time of 2015, which is the year we made detection, the work that the 4 of us had done had put Australia into a really front and centre type position in the LIGO project. And so we were really key players in that first detection. I mean, obviously we weren't the only key players. The Americans were a huge part of it and so on. And then there was the European detector as well. But we could have easily not been part of it. That's, I guess, what I'm trying to say. And I guess the work that we've done over those decades, and for me it's, well, a quarter of a century, and for David Blair it's obviously longer. It meant that we were ready to play that role. And once we achieved detection, then we were ready to play a part in the new field of gravitational wave astronomy. So I think that's what it recognised.
Could you tell us a bit more about LIGO and what the detection of gravitational waves meant for science?
So LIGO was a sort of vision of a few experimental scientists in America, and they designed a project that could potentially detect gravitational waves. And these are the ripples in space-time predicted by Einstein's theory of relativity. And they're very, very small. That's why Einstein thought we'd never actually detect them, because 100 years ago we didn't have the technology to get anywhere near being able to detect them. But of course a lot evolved over those 100 years, and actually by the time Einstein died, you know, we had lasers and so on, and quantum optics was developing. Things keep progressing in that direction, which is great, but the detectors were then started in the early 90s, like about 94, and we had first light in the late 90s. So it took a long time to build them. They're very big objects. They're L-shaped. They're interferometers, so they have two big vacuum tubes which form the L, and they're about 4 kilometers long. And we shine a very strong laser beam from the center down the two beams and bounce them off mirrors at the end, and then they come back and interfere. And if a gravitational wave signal passes through them, through the detector, it will alternately stretch one arm and then the other, and this will produce an interference pattern that we can discern a gravitational wave having passed.
And on what scale is that distortion caused by the gravitational wave?
It's so small. That's why it took so long to be able to do it. You know, it's like a 1/10,000th, you know, of a nucleus. It's incredibly small, and you know, it's like 10 to the minus 18 meters. And you know, you need a big instrument. You need a lot of subsystems in place to isolate every noise source. Every noise source that's around is going to affect the detector. So you have all these vibration isolation systems and so on. And we need very high laser power, and there's all sorts of noise sources from that. So all these things need to be factored in, improved, and we need to continue being able to measure smaller and smaller amounts to get greater sensitivity.
So the other side of your research is to do with general relativity. Could you give us a bit more about that?
The other half of my work, if you like, is on general relativity theory. And one of the areas I'm primarily interested in is the existence of singularities in space-time. And this is a sort of an ongoing important central field in general relativity, because there were very famous singularity theorems proven in the 1960s by Roger Penrose and Stephen Hawking, which said that we can expect under very general conditions on space-time to have singularities develop. Prior to that, it was thought we only had these singular solutions because they were very symmetric, like spherically symmetric, the black hole solution and so on. And people thought, you know, once we can generalize these and make them more, you know, like reality, then we won't get singularities.
Right. And so what might be like a physical representation of singularity? You mentioned black holes.
Yeah, so a really important central one is the black hole. So that's the end product of like a gravitational collapse. And you know, all the star burns up all its fuel, and then it collapses gravitationally. And if it's big enough, it goes on, and according to Einstein's theory, according to the solutions, and collapses to the center. And then it's formed, you know, this event horizon, and nothing from inside that can get out.
When the Big Bang Theory is described, it's often phrased as it started as a singularity. Is that referring to the same type of singularity?
The initial singularity, of course, is something of great interest to cosmologists, including myself and other people, astronomers and so on, because there are lots of different ideas about it now, and whether it just started from that beginning or whether there was a previous edition of the universe and there was multiple universes and whatever. So it is a type of singularity, and it is predicted by the singularity theorems. And this was the one contributed by Stephen Hawking. So it's a sort of cosmological singularity theorem. And that tells us that, with physically reasonable conditions on the universe, if we look back in time, then we will come to a singularity. And a singularity physically can be a place of infinite density. So you've got all this matter like in a star collapsing into a point. And similarly, the universe, it's going the other way in time. It comes out of the initial singularity. And so it's a really big open question, because what the singularity theorems actually predict is incomplete curves. And we call them causal curves because they're the curves that observers like us and photons and things move on. Right. And if they're incomplete, it means that the parameter along the curve ends at a finite value. So we know that something's happening, but the theorems don't tell us. Are they ending at a black hole type singularity, or what's going on? So we say that the singularity theorems are incomplete. And so one of the areas I work in is to try to complete the singularity theorems and to prove that these curves must end at infinite curvature.
And so to clarify, when these curves are incomplete, that means they sort of terminate at one side, or?
Yes. So going forward, for instance, in time, they'll finish at a finite value of this parameter. And just so you know, the Nobel Prize in 2020, half of it went to Roger Penrose, and it was for those theorems. So they are very, very important. They changed scientists' thinking around the world. Nobody expected singularities to be an inherent feature coming from the theory, and Einstein himself would not have enjoyed that result. I know that. But nevertheless, it's there, and it revolutionized science. Basically, the theorists knew that black holes existed well before the first candidate was ever identified in the universe. And at that time, the astronomy community thought it was laughable that we were talking, well, I wasn't part of it, but they were talking about, the existence of black holes in the universe. They were a kind of figure of joke, until that first candidate was found in 1972.
And what would it mean physically for these curves to be completed? So would that represent that a particle either never entered a black hole? Or?
The fact is that they probably they can't be completed, because if they've reached infinite curvature, we know that we cannot complete the curves. We can't do anything with them. They're whatever the observer is, it's obliterated at that point. So there's nothing you can do about it, but we want to show what are the possibilities for where these observers can end up. Is it just infinite curvature singularities, or is it some? We know there are possibly other types of singularities in the universe. We just don't have concrete examples of them yet.
Do we know what sort of properties these alternate singularities might possess, or?
Not really. We have ideas about it. We know that there can be sort of geometric singularities in space-time, things where the space-time kind of gets stitched together in a strange way, and things kind of blip out because they get to that point. But the curvature is not going infinite. It's just that they run out of space-time sort of thing. But that's a very indeterminate part of the field at this stage.
If you were to discover these alternate singularities, would knowing their properties make them easier to detect?
This is really a theorist's problem. We have to try to work out what sort of things they can be, just like we do with black holes. And if we could get to that point, then there'd be a hope of observers finding a way to find one out in the universe. but we're going to have to do the legwork. And normally it's the other way around, you see. Observers find stuff out in the universe, and then theoretical physicists and astronomers and stuff have to kind of work out what's happened and why it's happening. This is the other way around, and it's very unusual, but this will have to be the way for this particular problem. We're going to have to work out more about the range of singularities possible before people have a chance to look for them.
How do you think we can get more young people inspired to get into science and these sort of STEM fields?
That's a very important question, and it really will determine our future to a large extent. I personally believe we need a lot more young people going into STEM fields across all the sciences. And I think kids are put off at school, a lot of them, by the curriculum that we have. You know, they're not getting to see any aspects of modern physics, for example. Not that they're all going to become physicists, but it'd be so nice for them to get a grasp of the concepts while they're young and at school. Even if they go on and do other stuff, they've had a chance to see it. And we know that Einstein First is a program which addresses this. It starts in year 3 and goes up to year 10. And it gradually introduces, you know, modern concepts of physics and other related areas like climate change and so on at an early age, where and in a way that kids of that age can enjoy it. You know, it relates to things that they do otherwise, you know, their games and things like that. And then that slowly evolves throughout the years. And we find that the kids who are taking part in Einstein First come out at the other end. We do surveys, and they're really, really still interested in science, whereas going through the normal path, you know, just so many are turned off and just drift off, and we lose them all. And honestly, I think with the problems facing society in the decades to come, we're going to need a lot of young STEM scientists paving the way with changing things. And to do that, we need to keep them in the system. So Einstein First is really important for that.
If you were to give a piece of advice to some young person who's entering the field of physics or maybe science more generally, what would that piece of advice be?
Well, first and foremost, and this is advice I gave my own 2 kids entering university, I think a lot of people drift into degrees because of other reasons. In the end, it's very important to follow your heart. And that applies, once you're in physics, to that as well. I mean, there are quite a lot of different areas in physics and different tools used. You need to work out what excites you and follow that.
Awesome. Well, so thank you very much for your time today. And I personally learned a lot about singularity physics.
Thanks very much, Ben. Enjoyed it.